can't.
It's okay. It's okay.
Okay, so let me start my last lecture. And in the last lecture, I introduced the objects that we called V with a multi-particle label B. So B can be, say, 1, and B can be 1, 2, and in general it can denote P particles, right? And these objects were motivated by the OPE computation in string theory, and in particular using the pure spinor formalism, because this guy has a pure spinor inside. Say the definition is lambda alpha A alpha B, and their BRST variations are I wrote the BRST variations as follows, and in this lecture I'm going to use Mandelstam invariants. So the notation is S I1 to In is equal to 1/2 K1 plus Kn squared, right? So the BRST variation of this one becomes V S12 V1 V2, and we also had higher rank V's, and they had transformations like this, and then S123 minus S12 V1. So you can see that they satisfy some kind of algebra. You can start to see some structure here, and but now let's see. Oh, and I also said that these VBs satisfy Lie symmetries. In particular, V12 is minus V21, and then V123 plus V231 is 0, and so forth. There are other identities. So the fact that these guys satisfy Lie symmetries suggests us that we should try to come up with a convenient notation to make these symmetries manifest. And the convenient notation is as follows. We are going to denote a rank PV as a nested commutator. Let me just 1, 2, 3 like this, and then comma 4 like that, comma 5, and hopefully you get the point, right? It's something like that. So okay, this can be a bit messy to read, so let's just write down 2 examples. So V12 becomes V like that, so it manifests that it's antisymmetric, and V123 becomes V12 like that. So, and using this notation, it becomes a matter of using Jacobi identities for the code your well, it's a triviality. You just expand the commutators there, and the notation now makes the symmetries manifest, right? But you can so we have this notation now, and you can see that there is some ordering for the brackets, but you can ask yourself what happens with other orderings. So, for example, what is this one? Right? So why I'm saying okay? So this becomes 3, 2, 1. Okay, but now I'm going to motivate the mapping of these vertices to what mathematicians call planar binary trees. And one way to motivate this is to notice that what we are doing here, we have labels, and we are putting brackets around these labels. So we okay, bracket or parentheses, and I'm going to draw parentheses now. For example, we had this structure for that one, and this structure here for these ones. And mathematicians have played with this kind of things, and they enumerated them. So the number of ways to insert brackets around n labels, well, they counted it, and it's given by the Catalan numbers. So in particular, well, the Catalan numbers start as 1, 2, 5, 14, 42, and so forth. There is a closed formula for that. I think it's, well, I guess, okay, I have it. N plus 1. Something like that. That's the Catalan number. And mathematicians have also, well, there are like hundreds of interpretations for the Catalan numbers, and one of them is that one, and another interpretation for these numbers are the planar binary trees. So what are them? So for example, you have and then this guy here is this leg there is called the root, and has no labels associated to it. So and this guy is mapped to, well, in the mathematics literature they don't have V, obviously. They just have the bracket there. So you have this mapping between a tree and the commutator, and for example, for the next order, you have something like this: 1, 2, 3, then 1, 2, 3, and these are the two possibilities, and this bracket, the mapping becomes this one for this, and for that one it becomes this one, right? So 1, 2, and then there are 5 at the next order, and I think it's instructive to just write a few of them. So you will have something like 1, 2, 3, 4, and the other one is 1, 2, 3, 4. 1, 2. So these are the 5 trees that you can associate with brackets. Like, for example, this one is the canonical one, and so forth, right? So we have objects and we have trees. We have these V's and we have trees that we can associate with them. But we can do a little bit, well, we can play a bit more with them, because we know that they have BRST variations that look nice. So let's try to make those BRST variations look even nicer. So let's look at this guy, 1, 2, and then let's try to well, these vertex there will be associated to a Mendelssohn will be associated to a propagator like this, right? So it's associated. Okay, so this guy has a Mendelssohn S12 there. Let's interpret the vertex like this. It has a propagator associated with it. So let's define a new object, M12, from reading that diagram and dressing it with the propagator. I think it's hopefully you can read one. So right, and what happens with the BRST variation of this one now? Okay, so I forgot to introduce a notation. V with a single particle label. Let's also denote it by M, right? Simply because this equation here becomes more beautiful. So the simple definition, what it did for us was to remove the Mendelssohn invariant from the BRST variation of V. So you get something like that. And you don't stop right there. You continue. So let's see what happens with the next order, this one here. So let's write it. Let's write it here. So M1, 2, 3 becomes V1, 2, 3 over S12, S1, 2, 3. S12 is there, and S1, 2, 3 is that vertex, plus, and now that one, it's 1, 2, 3 over S2, 3, 1, 2, 3, right? And you can check using that BRST variation over there with these Mendelssohn invariants here, S12, S123 minus S12, that something very nice happens, because Q of M123 becomes M1, M23 plus M12, M3. That is, whoa, that's very nice, because the Mendelssohn invariants over there, they look at like, well, they were a bit strange, but if you divide if you use this definition here, now you have a nicer object that has a nicer BRST variation. And you can easily, you can continue like that for higher orders until you realize that you found the pattern. So and the pattern is that you get the deconcatenation of all the legs there, say M1. Okay, let's write it in a more abstract way. So the pattern is that Q of M, and now a multi-particle label. It can be any string of labels that is a sum over x, y equals b. I'm going to explain in a minute. Mx, my, where I'm simply deconcatenating this word in all possible ways by using x here and y there. So for example, 1, 2, 3 becomes, I separated the word 1, 2, 3 into 1, and then 2, 3, and then 1, 2, and 3. Those were the two possibilities. And in general, it works like this. So that's a convenient notation that people in combinatorics use. Okay, so now we have these objects, and for reasons that would take too much time to explain, these objects here, they are called Behrens-Gilly currents. Behrens-Gilly currents. And let me just say that by now we are used to the fact that we have 4 types of superfields, right? A alpha, AM, W alpha, FMN, and this guy here is associated to that one by simply we multiply by a pure spinor. But we can play the same game as having to define Behrens-Gilly currents for the other superfields, and we will have something like say, but the notation that we use in the paper is that we use calligraphic letters for the Behrens-Gilly version, but my handwriting is bad enough using just plain letters, and I'm not going to try to write the calligraphic version of these ones. But we have you can define Behrens-Gilly versions for all types of superfields. So okay, so yeah. I said this because if I have time by the end of the lecture, I'm going to say something very cool about this. But let's move on for now. What else we can define? Let's just define a new object E, 1, 2. Well, let's start using the notation. Let's define object EB, which is Q of MB. So we know what say for well, E1 is 0. It's not interesting, but E12 becomes M1, M2, and so forth, right? You just deconcatenate the word B like that. So that's a convenient notation to have for these objects. And okay, what else can we say about these M's? So the M12, you can easily convince yourself that it's antisymmetric, right? Because of this. But what is the symmetry of M123? It's not immediately obvious from the definition, but you can convince yourself that the M satisfy a symmetry that can be written like this: beta 1 alpha, where these betas are the same ones that Freddy was telling you about. They represent labels, sets of labels, and then that's -1 to the number of elements in the set beta, and M1, and now alpha shuffle product of beta transposed. And this shuffle product here is exactly the same thing that Freddy was explaining about the. I think he would write that as say this is omega, and then omega belongs to the ordered permutations of alpha beta transpose, something like this, right?
Yeah, the PI said that was preserving, order preserving.
Order preserving, yes. So, but in the mathematics literature, you find the shuffle product notation to say the same thing, and I think it's more convenient to. And the name shuffle means that just like when you shuffle a deck of cards, you say you separate a deck like this, and then you start to shuffle the two halves, and when you do this, you can see that you preserve the order in the sets alpha and beta like that. So for reasons, okay, that could become clear if I have enough time, this is a Behrens-Gili symmetry. So Behrens-Gili symmetry, like that. For any alpha and beta, this happens. So and there is something.
I meant, is it a sum over W? I mean, there are many ways of
shuffling. Yeah. But by this I mean the sum.
Oh, you mean the sum?
Yeah, I'm compactifying notation, but because. Yeah, let's just clarify that. So, for example, let's just do one example: 1, 2, shuffle, 3, 4. I don't know if is that clear? Okay, no, let's. That's 1, 2, 3, 4 plus 1, 3, 4, 2 plus 3, 4, 1, 2. I simply move it the 3, 4 right there, and plus, and now I can what can I do? I can use 1. Okay, no, I'm sorry. What else can I shuffle here? It's okay. That's embarrassing. 3. No. 3, 1, 4, 2. That's another one. And okay, and there are 2 other ones, right? Yeah, I shouldn't have tried to do this. That's another one, and then 3. 1, 2, 4. Oof. Yeah. So in general, if you shuffle m with n, where m denotes the length of the word, you get m plus n factorial over m factorial n factorial terms. And so when I would use a notation like this here, I mean the sum over when m assumes those sets of labels. Ooh, okay. That's not exactly the same. You should wait just a little bit. The KK relations that Freddy was mentioning had an extra n leg somewhere. It was, well, you could write it as 1 beta n alpha, something like this. And then in the right hand side you would have the extra leg over there. But we are going to arrive at that symmetry very soon. Any other question? Oh, I was going to mention another property. Well, it's equivalent, but it is not obvious that expression there is equivalent to the following one: m a shuffle b equals 0 for any words a and b. That is very well. I thought it was non-trivial, but in the mathematics literature, this symmetry is called alternal symmetry. That's related to the mode theory of Ekal, but that's a random observation that this way of rewriting the Berensky symmetry is it will be convenient later on if I have time. And another observation is that the set of something that is very similar to what Freddy was describing this morning, the set of 1 over z12, z23 until z p minus 1 p. So we don't close the cycle. So let's denote this as z12 until p. Again, we don't close the cycle to get some Parky-Taylor kind of cycle. This object here satisfies the same symmetry as that one. It's a Berensky symmetry, or equivalent, it's a alternal mode. It's and to prove that you need to use partial fractions identities. So that's an observation that if I have time at the end of the talk, I'm going to use it. So let's not forget that we are computing amplitudes, and the combinatorics here is nice, but we are computing amplitudes. But in the end, amplitudes, you will see that they are very combinatoric friendly objects. Okay, so in the first lecture, I said that if you compute a string amplitude, in the end you can do the following. You set the string size to 0, and after you do that, you recover the field theory amplitudes. And in this set of lectures, I'm focusing on the Superstring states from the open string. So let's see what we can do regarding this one. So you may think it is strange that I'm going to discuss Superstring theory amplitudes before computing the string amplitudes and then setting alpha prime to 0. But what I'm going to show to you is that the cohomology structure of the pure spinor superspace is so constraining that you can guess the amplitudes here in field theory by simply you can guess them. And so if you can guess something, let's do it first. So now I'm going to discuss the Superstring amplitudes. But what will be the starting point of the guess? We know in the end that the string theory will give rise to Superstring amplitudes if you set alpha prime to 0. But what were the elements that we had in the string amplitude? We had at tree level, we had these VBs, and that's all. That's all we obtained from the OPE computations. We had this guy, and the string amplitude will be in general it will be associated to you have some VBs and some Z's in the denominator, and then the Kobayashi factor, which I'm going to explain later. But in order to guess what the outcome of taking the alpha prime to 0 limit of this expression, we just need to know the elements in which the answer will be written. And the only other thing that will survive in the alpha prime to 0 limit are Mandelstam invariants. In the end result of this reasoning is that we should be able to compute Superstring or guess Superstring amplitudes using only the VBs and Mandelstam invariants. Let's do that. Okay, the 3-point is trivial, right? The 3-point function in amplitude in Young-Mills, if you just use the prescription, is that one, where this bracket here means it doesn't mean any path integral. It just means that we have the zero modes of lambdas and theta variables here, and we use the lambda 3 theta 5 measure or prescription to evaluate the component expansion. Right. So, but what about the 4-point amplitude in Young-Mills? Let's get some intuition from the cubic graphs. So the 4-point amplitude in the color ordering 1, 2, 3, 4 has two cubic graphs. It's that one and this one. 2, 3, 4, 1. And okay, so let's try to construct something. Oh, and by the way, I should have mentioned this. We know that the only elements that we are going to use are VB and S, the Mandelstems. But what kind of principle can we use to guess how to write some combination of these guys? And the principle will be BRST invariance in superspace. And once you realize this, and you know the V's, and you can convince yourself that V12, V3, V4 over S12 plus let's do it like V1, V23, V4 over S23. Let's see what happens with this guy here. Let's compute the BRST variation. That's our ansatz for this amplitude, simply by looking at the structure of the diagrams, and well, it's a kind of intuitive thing to do here at this level. So we compute the BRST variation of that one, and we will get V1, V2, V3, V4 for that one, and now minus, because the Q anticommutes with V1, so minus V1, V2, V3, V4, and that's 0. So we found a BRST invariant expression for that guy. And once you compute the component expansion of this object, since you know the theta expansions of the superfields, and you can use the lambda 3 theta 5 measure, you will find that it correctly reproduces the 4-point amplitude from field theory. Let's do one more example until before I write down the general answer. Let's do 5 points, just to get the intuition. I think you can, but it will be BRST equivalent to this expression. I don't really remember the other expression, and if there was one, but the claim is that, well, and we are going to see that for 5 points. For 5 points, I know the two forms of the amplitudes that are BRST equivalent. But the claim is that BRST invariance fixes the amplitude completely. And if you find two expressions that are BRST equivalent and have the same kinematic pole structure, then the claim is that they are equivalent. And once you compute the pure spinor bracket, they produce equal results or proportional. And this principle here, well, it has been tested for arbitrary number of for higher or for arbitrary high orders at 3 level, and we see the same principle at 1 loop and 2 loops and even 3 loops. That BRST invariance in 10-dimensional superspace is very constraining to get these amplitudes. And it was not obvious once you started to study the pure spinor prescription, but in the end, playing with these objects and trying to simplify things, that's the structure that appeared. Okay, so the 5-point amplitude has 5 can be described by 5 diagrams like this. So cyclic 1, 2, 3, 4, 5. And after you play a bit with these guys, you can come up with the following ansatz. For 5 plus cyclic. And you see that the mapping is intuitive. You look at this diagram and you associate, well, you can see. And you can convince yourself that this is BRST closed. I won't do the computation, but it's easy to check. And once you evaluate the pure spinor bracket, compute the component expansion, and compare with the result from the literature, you get that this is correct. It's okay. And so we computed the 5-point amplitude without much effort. We guessed it. And you can go on like this forever, but we don't want to do that. We want to find the general pattern. So let's use this definition here. Let's write down. Let's write down something and then
where is the integration over the potential?
what?
Where is the integration in terms of the potential?
There is no integration.
Okay, so
There,
where you
where
so why it not need to do that?
well, because you can think of these as being the field theory limit of the string integrals. So you evaluated the integral, so they are gone already. So and there is nothing else that you can do actually. Okay, let's give up. So if you see this definition here, E12, M1, M2, which is V1, V2, and if you remember the 3-point amplitude that is here, you will find that, well, this is E12, V3, right? And so let's generalize that. So let's say that the amplitude 1, 2, n is E12 n minus 1 Vn. And this is BRST closed. Let's just I talked about the Catalan numbers, right? And it's a known fact that the three-level amplitudes have the number of kinematic poles in a three-level amplitude is related to the Catalan numbers. It's Catalan number of n minus 2 or something, or n minus 1. But and you can see from this expression here and the definition of E over there that you also get the Catalan numbers for the number of poles. Let's. Is that clear or too difficult to see? Or let's see what we get, for example, for 4 points. 1, 2, 3, 4. That is E1, 2, 3, V4, and E1, 2, 3 is M1, M2, 3 plus M1, 2, M3, M4. Right? So this is the expression we had before, so it's okay. And there are two different poles here, S12, 1, 2, and S23. Let's just see what happens for the 5-point amplitude. It's 1, 2, 3, 4, V5 with the pure spinor bracket, but it's M1, M2, 3, 4 plus M1, 2. I'm just deconcatenating the word. M1, 2, 3, M4 multiplying M5. And what are the number of poles here? This one contains 2 poles because of that expression. This one contains 1 pole and 1 pole, so you multiply it, you get 1. And these 2 poles, so you get 5 poles. So the Catalan number is being respected. And you can actually write down the formula, the recursive formula to count the number of poles here, and you get exactly the recursive definition of the Catalan number. So the number of poles work out. You can check that this is BRST closed, right? Well, it's not that complicated. But what about the cohomology structure of this amplitude? Are these guys for some chance BRST trivial, BRST exact? Could it be that case? For example, you might worry, and you should worry, that E12 is defined as the Q BRST variation of M12, and V3 is BRST closed. So I just kind of proved that say M1, M2, M3 is BRST trivial, right? Because this M1, M2 is Q of M1, 2, like that, and then M3, but M3 is closed. So you can say that this guy here is the BRST variation of that combination, and you would get 0. But it's illegal to do that for 3 points, because M1, 2 so M1, 2 was V1, 2 over S1, 2. And if you remember from Freddy's lecture, the 3-point Mandelstam invariants are 0. So it's illegal to write down for a 3-point function amplitude M1, 2, because you are dividing by 0. So that is why you cannot do this for 3 points. It's illegal to have this object M1, 2. So it's truly in the BRST cohomology. And for example, what about this guy? This guy is also Q of M1, 2, 3. And V4 is BRST closed, so you can do the same thing. And you can say, okay, this is BRST trivial. But M1, 2, 3 contains S1, 2, 3 in the explicit solution. And for 4-point kinematics, S1, 2, 3 is 0. So you cannot do that for 4-point kinematics. And that is how you avoid BRST exactness of this answer there. So the amplitude is truly in the BRST cohomology. But to address Bruno's question, you can see that I wrote the 5-point amplitude here, like that. So now, well, I think we can start using the M notation here. So the amplitude here is M1, 2, M3, M4, 5 plus cyclic permutations, and this expression here is not the same as that one. So what can you do? It's not naively the same, but it's BRST equivalent. Why? Because, for example, look at this term, M1, M2, 3, 4, and then there is this M5. So let's move this M1 down there. So you get something like M2, 3, 4, M5, M1. But M5, M1, now that we are in 5-point kinematics, this guy is E51. So M2, 3, 4, E51, because I'm allowed to divide by the Mandelstam. And this guy is Q of M51. But remember that these guys are inside the pure spinor bracket. So you can do integration by parts, BRST integration by parts. So this Q there, so if you do that, you get E234 M51. And now if you expand the definition of E234, you will get M2, M34, and then M51, and then another term. And you can see that this term is one of those permutations. So what you show is that this expression here is BRST equivalent to that one. And there are other expressions that contain the same kinematic poles and BRST closed, but you can always show that they are BRST equivalent. Okay, just I mentioned that symmetry over there, and let's just check some properties of these ansatz. Okay, so by now I think you should be more or less convinced that the endpoint amplitude in field theory is that expression. But let's I'm just going to mention another property of that amplitude, is that it satisfies the Kleist-Coif relation. It satisfies the Kleist-Coif relation that Freddie was talking about, and the Kleist-Coif relation is 1 alpha n beta, where alpha and beta it's minus 1 beta 1 alpha shuffle B transpose n. And how you can convince yourself that that expression satisfies this symmetry? You simply plug the expression there, say, and now I'm going to write it schematically like this. So the Young-Mills amplitude is a sum over m like that, and then v, but v is m. You simply plug this expression here in that equation and use these symmetries there, and you will see that it is satisfied just by using these symmetries. So these symmetries here, they already know about the Kleist-Coif relation once you use the m's in this particular form that is given by that answer, ansatz or answer. There are many more things that I could talk about these the amplitudes, like we have expressions that are not manifestly cyclic symmetric, and sometimes we have manifest cyclicity, like it was here. I was summing over the cyclic permutations, and you can go from one to the other by using BRST manipulations, and you will find the 6-point, 7-point, and so forth amplitudes in manifestly cyclic form. So, but I'm not going to have time to. So now we know about the field theory amplitudes, which are supposed to be the alpha prime goes to 0 limit of the string amplitude. So let's do the string amplitude now in the 10 minutes or okay, so yeah, okay, in 10 minutes it's kind of difficult to compute the endpoint amplitude, but let's try. The prescription to compute the amplitude is this one, which I wrote many times already. V1, then U2, U n minus 2, Vn minus 1, Vn. And we already did the 4-point amplitude some lectures ago. And the result was the following. That was Z2, then V1, 2 over Z1, 2, V3, V4, plus V1, V3, 2 over Z3, 2, V4, and everything multiplying the Kobayashi factor. And the Kobayashi factor, just to be complete, it's what you get from this computation. I'm not doing this computation, but that's the result you will get. It's I less or equal less than j, and then n, or in this case it will be n minus 1, but and then zij over sij. That's the Kobayashi factor. So okay, that's the 4-point amplitude. Let's see what we can do with it. Let's do something a bit trivial in the beginning. Let's convert the V's to the Barents-Gilly current. And doing that, we will get, well, say, let's do this. V12 is S12, M12. It's a trivial manipulation to do. So we get S12 over Z12, M12, and now I'm going to use the M notation for this guy. So M3, M4, and now I do the same thing there. So it's S23 over Z32, M1, M32, M4, multiplying the Kobayashi factor. But let's do another thing. We know that the amplitude is multiplying the Kobayashi factor, and it's inside an integral over Z2. So we know that the integral of a total derivative is 0, right? Let's see what we get from these identities. 0 is the derivative of the Kobayashi factor. And you will get S12 over Z12 plus S32 over Z32. And then that multiplying the Kobayashi, that is 0. So we are allowed to use that this guy is 0 inside the integral. So let's do it here. And I'm running, and if you do that there, you get something nice, because let's see. So you will get S12, well, the integral over Z12, and now this guy, well, I'm just going to use that one, and I will get M12, M3 plus M1, M23, everything multiplying M4 and the Kobayashi factor. So someone's clock already told me that it's 5 p.m. so I need to rush. And But what is this guy here? We just computed. We just guessed the result. This one is precisely the 4-point Young-Mills amplitude with this color ordering. So we get that the 4-point amplitude in string theory is proportional to the field theory amplitude. And well, this result is old, but so the 4-point string amplitude is now this integral S12 Z12, the Young-Mills amplitude 1, 2, 3, 4. Well, in the color ordering 1, 2, 3, 4, and the color ordering here will translate to the integration region of the Z2 variables. But so that's the 4-point result, and I obviously am not going to have time to oh, okay. Okay. No, there is the Kobayashi effect. Thank you.
What happened in the alpha prime zero limit?
So in the alpha prime to zero limit, you can guess, right? Because you already know what's going to happen to the integral. If I didn't do any mistake, you will know that the alpha prime to zero limit of this guy, what will it be? The string amplitude with this color ordering. It should reproduce the Young-Mills amplitude. That's the left-hand side. Now the right-hand side must be the same. So you already know for free that this integral, say, let's give it a name. It's f 1, 2, 3, 4. That's del Z2 Kobayashi over Z12 S12. In this limit, it must be 1. If it's not 1, you did these arguments are wrong, but it's correct. It's 1. You can check that. You can compute, and in this case, it's not that complicated. It's a gamma function, and you can explicitly verify. And if you change the ordering here, what you will get is, well, you will need to integrate over a different region. Say instead of from 0 to 1, it could be from 1 to infinity and something like that. And the evaluation of this integral will change, but it will change in precisely the way that is dictated by the BCJ identities. So I don't remember any identity by heart now, but say if you compute 1, 3, 4, 2, take the alpha prime to zero limit, and then the integral will tell you that this is, say, S something over, okay, I'm not going to write because it's going to be wrong, but it will be a BCJ identity. And that should be true, and it is true. So I'm just going to write the next amplitude very quickly. Well, since almost everyone got some 5 or 10 minutes, that's just that's my last lecture, so you won't need to I won't come. Okay. There are some things that you can do to get the 5-point amplitude, but I will skip those. But I will write some intermediate step that you get once you already used some tricks, which you will get this result here. It's V1 to 3, V4, V5 over Z12, Z23 plus V12, V43, V5 over Z12, Z43 plus V432, V5 over Z4332 plus the permutation of 2 goes to 3. That is already one intermediate step of the calculation, but it's something very beautiful already happened to get this structure here. It's related to the Lie symmetries of the V's and the Barents-Gilly symmetries of these guys. But let's just use another miracle that happens. The miracle is there is an identity that will convert these guys. So remember that in this 4-point case, the identity to convert V to M is trivial. But at higher points, it's not so trivial anymore, but it's true. Plus 2 and 3, that becomes S12 over Z12, S13 over Z13 plus S23 over Z23, M123 plus permutations. This identity here is very non-trivial, and it generalizes to n points. And I don't really understand why this is true. There must be some very deep reasoning related to the Lie symmetries, but it's true. This identity is true, and now so you can convert all the V's to M's in this expression, and in addition you can integrate. You can use the same trick of the integration over the Kobayashi factor to replace this term here by something that is S34 Z34, and you do this for all the other terms, and you will get a very nice result. You will get and then I think I will stop after. You will get that the 5-point amplitude is the integral over S12 Z12 S34 Z34, and then what we will get? We will get M123 M4 plus M12 M34 plus M1 M234 M5, and then Kobayashi, and then permutation 2 3. But now you should remember, I think it's there, right? That is the 5-point Yang-Mills amplitude in this color ordering. So what you get in the end is that the string amplitude with the canonical ordering here is the integral of S12, Z12, S34, Z34, and then the Young-Mills amplitude of 1, 2, 3, 4, 5. Plus 2 and 3. Kobayashi. So you explicitly evaluated the string amplitude in terms of kinematic building blocks, which are the Young-Mills field theory amplitudes. And notice that we didn't arrive at the result by first computing the string amplitude and then taking the alpha prime to zero limit. So now we can check that we did the computation correctly, because say you take the alpha prime goes to zero limit in this side, in the canonical ordering. So this integral here must be 1. And the other integral that will be multiplying the other permutation, the 1, 3, 2, 4, 5 must be 0. Otherwise you get nonsense. And that is true. You can check that these integrals satisfy this property. And now you can play with it. You can change the ordering here. When you change the ordering here, you do not change the ordering of the Young-Mills amplitudes that you found here. And there are 2 Young-Mills amplitudes. So 2 is n minus 3 factorial in this case. So what you learn from this computation, no matter what ordering you have here, you will be able to evaluate the field theory limit of that guy in terms of only 2 amplitudes, this one and that one. And that's the content of the BCJ identities. And if you evaluate the integrals in a different order than in the canonical ordering, you will get all the Mandelstam invariants that you need, that BCJ told us to in their identities. And these things generalize. And by now I think you can be convinced that whatever I said that works for 3, 4 points and 5 points, it works for n points. And the string result will be something like that. It will be some factors like these multiplying Young-Mills amplitudes and some permutations of n minus 3 factorial amplitudes. And that's the and I don't have time. I would say something about generating functions for all amplitudes at the same time, for both the field theory and the correlation of the string amplitude. But I just want to summarize what we learned here. In the first lecture, I told you that the RNS and the Green-Schwarz had some issues to compute the amplitudes because they didn't manifest all the symmetries that are there in the string amplitude, say the manifest spacetime supersymmetry and covariant quantization, if the formulas can be quantized in a manifestly Lorentz invariant way. And what we learned during these lectures was that we were just using these 2 facts. We were using superfields, so supersymmetry manifest in spacetime, and we had the BRST charge, which is the covariant quantization. And just using these guys and then playing with some combinatorics and all that, we solved the 3-point amplitude to all orders, just by using the symmetries, more or less. And so that goes back to the initial claim in the first lecture. And the hope now is that these kind of reasoning can be extended to loop levels, and we have evidence that at one loop and two loops things are working, and the future should contain more amplitudes to be computed, but the future should be good, and I hope that some of you may be motivated by how symmetries could solve this problem alone. And so that's it. I'm sorry about the overtime. Not really, but for three level, you can always say, well, there is the KLT relations to rewrite the 3-level amplitudes for gravity in terms of amplitudes for the open strings. So it's not needed in some sense, but
So what we were doing was computing the spectrum and understanding the excitations of the Heisenberg spin chain. And we started with the ferromagnetic spin chain, where by studying 1 and 2 particles, we could read off what's the energy of one particle, which is this. And this is a fancy way of saying that the energy, this is, I mean, only a crazy person would write it in this way if the goal was to write what's the energy as function of p. It's sine square of p over 2. Okay, you can write it in this parameterization, but the big advantage of this u is that the complexity becomes much more uniform. So e to the ip is a polynomial, is a rational function, energy is a rational function, s is a rational function. Everyone is rational and nice, and it's clearly a very good parameterization. Of course, physically what we care is epsilon as function of p. Is it okay? So this was the ferromagnetic, and then we went to the antiferromagnetic, and we saw that the energy per unit length was log 2. So let's start from where did we derive this from. So our, if you want, our UV description, the exact description that we have of the spectrum in our fundamental description is that the energy is the sum of 1 over uj squared plus 1/4, where j runs from 1 to n, where n is the number of magnons. So n equal L over 2 was what we did to go to the antiferro. It's a huge amount of magnons, right? Very good. And this is the energy, where these u's obey the equation that we wrote in this nice u plus I over 2 to the L, product of S matrices and so on, which after taking the log becomes L times arctangent of 2uj. So I'm destroying all this beauty that I'm advocating for these variables by taking the log, but the payoff was that we could treat these equations in a much better fashion. Minus, there was a 2, minus 2 sum over k of arctangent of uj minus uk equal 2 pi times an integer or half integer. As we said, it depends a bit on the number of particles, qj. And then it's clear that there is a maximum and a minimum value of this q, because all these functions are bounded. And we saw that for the antiferromagnetic case, we actually have no choice but to take for the antiferro, q's, j's had to go from minus L over 4 plus 1/2 all the way to L over 4 minus 1/2, such that if you take the biggest value and compute twice that value plus 1, you get L over 2. And then what we did was we said, well, what is a density? A density means that if I integrate rho of u from some u1 to a u2, what I should do is I count the number of magnons. Right? That's the definition of my densities. For any u1 and u2, I count how many magnons there are. Do you agree? So if I have u index j, which in a continuum I say it's u of j, I just promote the index to a function as usual, then what is the number of magnons? The number of magnons is just j2 minus j1, right? By definition, it's just the index j2 minus the index j1, which is just the integral dj, which is just the integral du 1 over du dj, in other words, dj du. Okay? This is, and therefore, this object is to be identified with a density. Okay? Just recalling this point, because I know that this point confuses people often, so I do want to emphasize it. Okay? Is this clear? So I wrote here this snake is the correct logic. Is it okay? Good. So now, and then what did we do? We took this equation, we took the derivative of this equation, and we got, you see the derivative of this arctangent are not very clear, but if you take the original form, where I write p in this form, you see, derivative of log of this, it's obvious that it's u squared plus 1/4 downstairs. So, and then we got L times energy of u plus some kernel of u minus v, which was convoluted with some density of v, equal to 2 pi times the density of v, and therefore, so minus here, and therefore we inverted, we found the density, and once you find the density, we plugged into the expression for the energy, which was the integral of rho of v times epsilon of v, and we got that this was log 2 times L. Okay? Good. So all this was just to recap. Is there any question about this? No. So now something funny happens. So, and I want to emphasize something more, that here for the ferro, I want to remind you that these excitations for the ferromagnetic, this here, this magnon, as we said, is a spin 1 excitation, a spin flip. In total, it goes from plus 1/2 to minus 1/2. The deficit is 1. So now let's do the following, and let's put n, let's put instead of L over 2, we put 1 less. Okay? So we put 1 less. So this state will have spin equal to 1 as well. Right? The total state has spin 1. Do you agree? Because we just put 1 less excitation. So we put 1 less magnon. The magnon has spin 1. We put 1 less magnon. The state has spin 1. Or minus 1. Okay? Compared to the singlet. Do you agree? Okay? So it has spin 1, which is the spin of 1 magnon that we are missing. Because we put 1 less than the vacuum. But now let's see what happens, which is funny. You see, I did not do this exercise in detail of working out what's the maximum and minimum. Okay, because that's a bit, we have to be very careful with arctangent. Does it go to pi or asymptotes pi? It's a pain. Anyone can do it. But it's very easy to see what happens if you have 1 less particle. Well, if we have 1 less particle, we have 1 less arctangent, which is decreasing. So this L. So this here, it's not L over 2, which would be what we have if we didn't have this, but it's L over 4 because these terms are fighting against the L over 2. But if I have 1 less, I can go 1 further. So if I have 1 particle, let me do in yellow, what would happen is that there will be a plus here, and here a minus. There is a bit more space now. Okay? So because of being L over 2 minus 1, I subtract less things. So when I send the u to infinity, I have some more space. Okay? So how much space do I have? Now I have L over 2 plus 1 options for the Qj. So something funny is happening. I have before here, I had L over 2 options to choose and L over 2 particles, so there was no option. Each particle goes to each mode number. Do you agree? Now, because I put 1 less particle, I got 1 more room. So I have 1 more option and 1 less particle to put. So it's kind of fun because what happens now is that I choose my mode numbers and I put the maximum. And I have to choose 2 not to use. You see? So I will choose to use all these mode numbers from this list, and 2 of them I don't use. Right? Remember, I have to pick different mode numbers. Otherwise, the roots are the same, so I have to pick different ones. But I can choose L over 2 plus 1, but I only have L over 2 minus 1. So 2 I'm not choosing. So these ones, let this be our Q's. And these ones are what we call holes. Because we choose everyone, we use all the Q's, and these ones we do not use. So you start to see this fractionalization that I was hinting. We put 1 excitation, there are 2 holes appearing here. Okay? Good. So now, good. So what does it mean? It means that my Qj Okay? It means that my Qj is now equal to some Q minimum plus j. So it grows linearly, but then when it gets to the hole, it jumps. So plus a theta function when j passes by j1. So when j passes by j1, it jumps by 1. Plus another theta function when j passes by j2. Then it jumps again. Right? So now when I repeat my derivation, well, what's the derivative of j with respect to u? That's the density by definition. But now I have to take the derivative of this object here, which will give me a delta function. Is it okay? So because of these terms here, let me tell you what is the outcome of this. Because of these terms, what happens now is that in this equation I get here plus 2 pi delta. Now I have to introduce some notation and we'll explain you what this is. U minus theta 1 plus 2 pi delta of u minus theta 2. Okay? These are the extra sources from because of this. Okay? Now I have to define what these thetas are, which is kind of simple, but it's kind of a bit unusual, so please pay attention to this part. So the idea is the following. Define the so-called counting function f of u, which is defined as basically what gives bit equations. It is just 2L arc tangent of 2u minus 2 sum up to the number of particles of arc tangent of u minus uj. Now, it's again, so what you do is you take a solution to bit equations. So you solve bit equations, and you construct this function of u. Okay? Now what happens to this function? What happens to this function is the following. If we think of this function as a function of u, and we think of this as a function, and we plot this function f, what will happen is that this function is something like this. And now we solved bit equations, we put these uj's, and now we think of it as a function of u. Whenever u goes through a value of a beta root, when it's equal to u1, when I put here u1, what do I get? I get the corresponding mode number q1, because then this is bit equations. So when I am at u1, I read here q1. When I pass by the root u2, I read here another integer q2, right? q1, q2 are the first integers that I'm using, and so on. Do you agree? So now in these x's I put all the integers. So I just take this grid and flip it up, and there are 2 points that correspond to my 2 holes. Let it be this and this. Okay? Now these 2 holes correspond to some point here, which is not a beta root. It's also an integer, but it's the one we did not choose. So this point I call theta 1, and this point I call theta 2. Right? All other points, when these lines intersect, all these other points are beta roots. These are the only ones. Right? Is the definition clear? We define this function. The function goes and passes by all the particles, and then it also. So when the function is an integer, you make a noise. Click, 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 click. Most of the time it's a beta root, except when you choose an integer that it's not in your list, the noise is meh. That's a hole. Right? So theta 1 and theta 2. Is this clear? So this is the definition of my holes. So the holes, by definition, they obey the equation that f of theta 1 is equal also to an integer. Let's call it q tilde 1, which is not in the list of the q's. But it's an integer. It's between minus q max and q max, but it's not. It's the one we did not choose. And similarly for theta 2. Yeah? It's okay? That's our definition. Good. But now we know what these thetas are. They are just the image of these unchosen mode numbers as a continuation. And now we have to solve this equation. So how do we solve this equation now? Yes? Yeah, it's obvious. Yeah, but yeah, if you want, yeah. The way to think, one way to think is the following: what is this function here? It's a function. This function here, the derivative of this function, by definition, is equal to the density of particles plus density of holes. Because if I count both particles and holes in the same way, then the derivative of this function tells me how dense they are. And therefore, another way of deriving this equation is starting with this definition of f, taking the derivative of it, equating to density of particle plus holes, and then holes, because they are peak, they are just two delta functions. Anyway, it's plausible, right? It's the only possible value associated to theta, so let me... it's a technical detail. It's more or less trivial. I think it's trivial. But... yeah. N here is the number of particles of solution of bit equations. This n is L over 2 minus 1 here. For this example that we are doing, n is L over 2 minus 1. Right? So we solve bit equations, and then we construct this function. So in this example, it's n over 2 minus 1. If we do this example with L over 2, which was the ferromagnetic example, this function, there will have no yellow lines. All the points will be used. There will be no holes. There are two holes because we removed this one. So we got one less particle and one more space. So we got two holes. If you put minus 2, you will see that you'll have 4 holes, and so on. So they come in pairs. Okay? But you see, the way to think is you have the U's, and you put U1, U2, U3, U4, U1 million, and then you jump, U1 million and 2. What's the hole? It's right in between. It doesn't matter much how you define. Any smooth definition will give more or less the same. Yes. 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 Yeah, exactly. Absolutely. Good. So now we have this. So how do we solve this integral equation? Again, the point was that if we managed to solve this equation, which we did, we just inverted this kernel in Fourier, and we inverted this kernel and acted with the kernel on epsilon. Now we can just solve, right, rho equal rho plus delta rho, and act with the kernel on the delta function instead of acting on epsilon. It's not more complicated, right? So basically, the solution is that rho is equal rho for the ground state plus, let me write like this, delta rho that depends on u minus theta 1. I can solve for each perturbation separately, plus delta rho that depends on u minus theta 2. Right? Where this delta rho obeys the equation that delta rho plus kernel convoluted with delta rho is equal to delta function. Right? So the Fourier transform of delta function is 1, and we just solve it in the same way, and in this way we get delta rho of u and well, yeah, we just solve it. Right? So the Fourier transform of this delta rho is just what? It's 1 divided by 1 plus, and the Fourier transform of this kernel, which was e to the minus absolute value of k. Right? Before the Lorentzian was e to the minus absolute value of k over 2 upstairs. Right? Good. So this is what this is. And now we can do the following. Now we can compute the energy, which will be E0, the ground state energy, plus the integral of delta rho of u minus theta 1 times 1 over u squared plus 1/4. It is just the integral over the full density, plus the same thing, integral delta rho u minus theta 2, 1 over u squared plus 1/4. Right? So you just compute this integral, you found this function, you just compute this integral. What is this quantity? This is what we call epsilon of theta 1. This will be the energy of my spinon. And this will be the energy of my other spinon. I have a pair of spinons, and this is epsilon of theta. Do you agree? So I can compute this integral, and I'll just add it to the table, what this is. And this, if I remember correctly, it's 1 over cosh. Do I have it written? Great. So if you compute this, for a spinon, the energy is 1 over cosh of pi u, or pi theta if you want. Let's use thetas for spinons. Pi theta. Of course, as it is, it doesn't mean much because we have to compute p of theta, and then we will know what epsilon of p is. For now, just know as function of this theta, this impurity, it's 1 over cosh. Like here, it was this. Okay? Okay, now we want to compute p. So now how does it work, the computation of the momentum? There are two ways of doing it. One way is in the same way that you integrate the density with energy, you can put here p and compute. Yes?
Can you only create spinons in pairs?
Yeah.
Oh,
Yeah.
does that mean?
That means that spinons are spin 1/2. And because we have to change the spin by 1, we need to create them in pairs. So these excitations are spin 1/2 excitations. You see that we decrease the spin by 1. How? By 2 excitations. So the spin is 1/2 of each of them. So we try to decrease by 1. It was not like we said, let's put 2 particles. All we said was, let's put 1 less magnon. Right? That's all we said. We said, instead of putting L over 2 magnons, let's put 1 less magnon. And then we saw there were 2 particles there. So no, we didn't ask.
Yeah, the support got bigger.
Yeah, the support got bigger. There was 1 less particle, so we got 2 holes. So this is what people call the particles fractionalized. It's like a magnon became 2 spinons. Okay. Now, what do? We do the following. We write our f of u. Okay? And f of u itself, I can now compute it by saying that I have my definition of my f of u. And I plug in f of u the density that I just got. Okay? So I plug this definition of f of u. And I say that f of u is 2L arctangent of 2u minus twice the integral of rho of v, the full rho, times this arctangent of u minus v. Right? Where this rho is rho 0 plus delta rho of u minus theta 1 plus delta rho of u minus theta 2. Or in this case of v. Okay, as function of u, it's this. Of course, we are going to put u instead of v instead of u. Right? So we know what this function is. Right? Because we computed this density, so we can compute this function. It's not just an abstract construction. I can just compute it and plot it. So now I can impose that I can compute f of theta 1 to find where theta 1 is, because theta 1 is quantized, theta 1 and theta 2. Like the magnons have to be quantized, theta 1 and theta 2 also have to be quantized. The spectrum is still discrete. So I compute f of theta 1 and say this f of theta 1 must be this q tilde 1 that we said. And similarly, f of theta 2 must be q tilde 2. By definition over there. And therefore, when we do it, what happens is that this equation now, I plug theta 1, and you see that what happens, does this generate? I put here theta 1, I put in what I get here theta 1, and there are some terms that only know about theta 1. This rho 0 also contains the length L. So there are some terms that are L times some new function, P effective of theta 1. And there are terms, when I put theta 1 in this convolution that knows about theta 2, that look like an S matrix between theta 1 and theta 2, that are what I should call an S matrix. So I call these terms plus 1 over I times log of an effective S matrix between theta 1 and theta 2. But now you see, by looking at these equations, I read off what is P and what is S. And what is the meaning of these terms? This is just saying that a spinon goes around the spin chain which has length L and acquires some phase, plus it scatters with the other spinon and acquires some phase by the scattering of the other spinon. So because I know that the meaning of these equations is just this meaning here, I read off the S matrix as being this term here, and I read off the momentum as being what I call here P effective. This is the momentum of the spinon. Right? Do you agree? Now it's a question of just working out these Fourier transforms and so on, but everything is super explicit. Right? So again, we know this. Rho 0 and delta rho, we know them. In Fourier or in position, you can compute them. We just compute this function. At theta 1, by definition, it must be q tilde 1 and q tilde 2. At theta 1 and theta 2, the integers we did not choose. This gives us some equations for theta 1 and theta 2 that are of the form of bit equations again. And if we will do it for many particles, they would again be the form of bit equations with many S matrices exactly as it should. Okay? So we can now read off the S matrix and the momentum of this excitation. So let me just tell you what this gives, which is kind of fun. So 1 over cosh was the energy. Now if you do the Fourier transform there that gives the momenta, you get arctangent of sinh of pi theta. This is what you get. It's very simple. But now you are very curious. You want to put them together and see what is epsilon of P. What's the dispersion relation of a spinon? Right? You are curious. You want to plug both together and ask, in Mathematica, what is epsilon of P? Right? Any guess? It's not very complicated. It's pi over 2 cosine P. It's kind of a complicated way, once again, of writing a simple dispersion relation. You see, it's also non-relativistic in the sense that it goes like P squared. Remember, this 2, epsilon was sine square of P over 2. It's a bit different, but not so different. But then you ask, what is the S matrix? And the S matrix is more interesting. And actually, I don't think it fits here very well. So let me put a star and write it somewhere else. And this S matrix, S of theta 1 minus theta 2, let me define this quantity as being theta. It depends only on the difference. Okay, just the S matrix of two spinons in the antiferromagnetic is given by gamma function 1/2 plus I theta over 2, gamma function 1 minus I theta over 2 over gamma function 1/2 minus I theta over 2, gamma function 1 plus I theta over 2. That's how spinons scatter with each other. So now you see why this theta is useful. After all, it's not just something crazy. Of course, if I would now imagine writing what's the S matrix of P1 and P2. Now it would not be S matrix of P1 and P2. Here for theta, you should plug arc sinh of, you should invert that relation and plug here some monster. So it's once again the most economical way of writing the three elements. The three elements over there. So so yeah, that's it. So I think maybe, there were a few more comments I could say about showing more precisely that these objects have spin 1/2, not only have spin 1/2, but symmetry is restored in the sense that we are in the antiferromagnetic state. So now we did not pick any vector. This state is a singlet, right? So now we should be able to scatter two of these spinons if they are spin 1/2 particles. Now I have two options. I can scatter both of them with spin up with each other, or one with spin up, one with spin down. And this S matrix is what we get if you scatter both of them with spin up. So we should, right? So because this is a state with total spin 1, so it's two spins 1/2 in the symmetric representation. How can we find now two spinons but in the antisymmetric representation, scattering with each other? Okay? So this could be done. Indeed, we could now go about and trying to find this state, and we find something nice. We find some state which describes two excitations. They have the same energy, the same momenta, which allows us to say they are the same spinons. Their S matrix differs by that one by a simple rational function, such that when we put them both as a matrix, saying what is the S matrix as a matrix of spin up and down, It's not a random matrix. It's a matrix that beautifully obeys Yang-Baxter equation as a matrix equation. And then your picture is complete. Spinons are spin 1/2 objects. They scatter with a matrix. The matrix of their scattering factorizes as it should in an integrable model. And you basically know everything you want to know about spinons. You know their S matrix, you know their energy, you know their dispersion relation, you know everything.
But that state with the spinons cannot process one by one.
That's right. Well, yeah, but okay, we have the barbecue in 9 minutes. But so that state should not decrease the spin, should have the same spin as the ground state. So what happens is that to find that state, we have to go to these complex solutions that I told you about, that this solution admitted. And right now we are only looking at real solutions. And it turns out that there is a particular complex solution, a very simple one, that describes exactly that singlet pair of two spinons, which is exactly degenerate with this one. Okay. Very good. So tomorrow we go back to Wilson loops and n equals 4. I will start by just saying what would be the analog of this analysis in n equals 4, not doing it in detail, but quoting the results, saying this is what we get. This is the dispersion of my n equals 4 spinons, which is flux tube excitations. Here is their S matrix. Let's use them for solving scattering amplitudes at finite coupling by using them to construct our pentagons and flux tube energies. Very good. Thank you.